In this video, we will go through how to do Bohr-Rutherford diagrams. Bohr-Rutherford diagram is a way of representing the atom. This was derived by the Danish physicist Niels Bohr, who came up with this idea of the planetary model of the atom. In this model, electrons are arranged in orbits that surround the nucleus. Niels Bohr, in his model, suggested that electrons move around the nucleus in orbits like planets around the sun. So this is where this planetary model comes from. You have your nucleus, which is like the sun at the center of the solar system, and then the electrons, which are like the planets, which orbit around the sun, or in this case, the nucleus of the atom. And then for the electrons, he suggested that each electron in an orbit has a definite amount of energy. He also suggested that the further away the electron is from the nucleus, the greater the amount of energy it has. So electrons that are close to the nucleus have a low amount of energy. Electrons that are further from the nucleus have a greater amount of energy. And as a result, electrons are more stable when they're at a lower energy, thus closer to the nucleus. He also suggested that electrons cannot exist between orbits, but can move up or down from one orbit to another. So electrons can only exist in these defined orbits. They can't exist in between an orbit, but electrons can move from one defined orbit to another by absorbing energy, and then can move back by releasing that energy. Now, these suggestions about electron behavior, combined with Rutherford's nuclear model, we can use this information to summarize the position of all subatomic particles in an atom using Bohr-Rutherford diagrams. So how do you draw a Bohr-Rutherford diagram? So first you begin by drawing a circle. The circle represents the nucleus. Within that circle, you write the number of protons and the number of neutrons inside the circle. For protons and neutrons, you can use the following short forms. The symbol for a proton is a p superscript plus. So for example, if there are 11 protons, you would write this as 11p superscript plus. The symbol for a neutron is an n superscript 0. So for example, if there are 12 neutrons, you would write 12n superscript 0. And then for the electrons, you use parts of circles or whole circles to represent the electron shells, or the orbits where the electrons will be found. The electrons themselves are shown as small filled circles on the shell. Each shell can hold a certain amount of electrons. So the first orbit, or the first shell, is the first circle surrounding the nucleus. It can hold a maximum of 2 electrons. The second orbit is the second circle surrounding the nucleus. It can hold a maximum of 8 electrons. So once a total of 8 electrons is reached in this orbit, it is considered full, and then remaining electrons have to be put into another orbit, or you start to fill a third orbit. So the third orbit is the third circle surrounding the nucleus. It can hold a maximum of 8 electrons. And the fourth orbit or shell is the fourth circle surrounding the nucleus. It can hold a maximum of 18 electrons. In our case, we'll just be putting in 2 electrons. Once an orbit is full, you must draw another orbit and continue filling it with the remaining electrons. So let's draw a few examples here. We'll start with the example of sodium, and we'll draw a Bohr-Rutherford diagram for this element. So we have to get information about subatomic particles, so we have to figure out number of protons in sodium, number of electrons, and number of neutrons. So all this information can be determined from the periodic table using atomic numbers and atomic mass. So remember that number of protons is equal to the atomic number. And in this case, the atomic number for sodium is equal to 11. So sodium has 11 protons in its nucleus. Now, number of electrons is equal to the number of protons in a neutral atom. And in this case, since sodium has 11 protons in its nucleus, it will have a total of 11 electrons. The number of neutrons is determined by taking the atomic mass and subtracting the atomic number. So in this case, the atomic mass for sodium is 22.99. We'll round up and say 23. Minus the atomic number, which is 11. So this gives us a total, I guess if we were to do this math here, we'd have 11.99 neutrons, but you can't have 0.99 of a neutron, so we'll round up to 12 neutrons. So in this case, sodium will have 12 neutrons in its nucleus. So now we'll draw our Bohr-Rutherford diagram using the information about protons, electrons, and neutrons. So we'll start by drawing a circle. This circle will represent our nucleus. In the nucleus, we will write the number of protons using our short form for protons. So we have, 11 p superscript plus. And then we will write the number of neutrons, which is 12. So we'll have 12 and superscript 0. And then now we have a complete nucleus for sodium. And so now we'll add in electrons. We have a total of 11 electrons that we have to add to our diagram. So we'll start by drawing our first circle. This will be our first orbit, and that first orbit can hold a total of 2 electrons. Electrons also like to be as far apart from each other as possible, unless they're forced to be paired up. So in this case, these 2 electrons are going to be on opposite sides of the shell, or the orbit. So we've added in 2 electrons. This first orbit is full. We have more electrons that we need to add in. So we'll draw a second circle to represent that second shell, and then we'll start adding in electrons. So when we add in our electrons to the second orbit, we add in 1 at a time. So in this case, we'll add in our first, and then we'll add in our second at our next side, away from that first electron. Third electron will be added to the other side. Same with our fourth. So we can have 4 unpaired electrons, and then once we hit 4, and if we have to keep adding in more, we start pairing up our electrons. So we have to get up to 11 electrons, and we're not there yet. So we'll add in our 5th electron, 6th electron, 7th electron, 8th electron in the second orbit. This orbit is now full. We've added a total of 10 electrons. We still have 1 more electron to go. So we're going to draw 1 more circle, and we'll draw in our 11th electron in that third orbit. And this is now our Bohr-Rutherford diagram for sodium. For fluorine, we'll follow the same procedure, but this time when we make our Bohr-Rutherford diagram, we'll use half circles instead. So for fluorine, we'll need to figure out number of protons, number of electrons, and number of neutrons. So for fluorine, our atomic number in this case is 9, which means the number of electrons is going to be 9. The atomic mass for fluorine is it's 18.99 or 98, depending on the periodic table that you look at. And that will leave us with 9.99 neutrons, and we'll round up and we'll make it an even 10 neutrons. So fluorine will have a total of 10 neutrons in its nucleus. So now we'll make our drawing, but for fluorine, but when we reach the electron shells, we'll use half circles instead of full circles. So for the nucleus, we're still going to draw a full circle. So here's our nucleus. We'll add in number of protons and the number of neutrons into the nucleus. And then now we'll add in our electrons, and we'll just use half of a circle. For the half circle, when we use this method, instead of drawing circles to represent the electrons, we will simply write in the number contained within the shell, and then write the symbol for electrons next to that number. So the symbol here, so we have 2 electrons in the first shell, and then we'll simply write an E with a superscript negative to represent those electrons. And then these are the electrons in our first orbit. So we've added in 2 electrons. So we still have another 7 to go. So we'll draw another half circle, write in that number 7, the remaining electrons, write an E, and then complete our half circle. And then this is a Bohr-Rutherford diagram for fluorine as well. So using half circles and numbers instead of circles for the electrons. So that is the end of this video for Bohr-Rutherford diagrams.